Here we're looking at section 1.3. It's a summary on defining functions. So we will talk about them verbally, symbolically, numerically, and graphically. We've already talked about the verbal, symbolical, and numerical aspects in the previous two sections. So we'll get a chance to look at those and again at the graphic definition of a function. We're going to distinguish between discrete and continuous. I did mention those two terms in the last section. So we'll finish and flush out those two definitions for discrete and continuous. And we'll graph using technology. Cool. All right. So when we graph, we're going to be graphing these on a rectangular coordinate system. A rectangular coordinate system is a set of two axes, an x-axis for the input variable, a y-axis for the output variable. And we may not always use letter x and y, however, horizontal is always input and vertical is always output. Okay. So I already kind of started this example in one of my in-person classes, so sorry there's a little drawing in my book already, but it's not finished. So let's continue off on this one. We were looking at the textbook example on the very first page, section 1.1, with the cars and the time situation. And we wanted to graph this information. So we have to graph it in the 24-hour clock. And so our time is 0, 100, 200. I couldn't fit all of those, so I just kind of cut off the zeros when I was labeling mine. But 1 stands for 100 for 1 a.m. and so on. And then we're going to go all the way up through 2300 at the end there. All right. So I plotted a couple ordered pairs. So in the range, I counted by 100 on each of these. And so the 7, 24 is graphed, the 8, 212 is graphed, and then it looks like I already have the 9, 384 graphed as well. So I need to graph all the rest of them. So 10, we're going to be at 426. So this is 400, about a quarter of the way up. I'm not going to label all of my dots, just going to draw them in. 11, we need to be at 538. 12, 497, so just below 500. 13 at 384. So 384 should be roughly the same height as it was before at 384 right here. All right, then we need to be at 337 and 285. 278, so a tiny bit lower. 302. 427. And again, I'm estimating where this would be, knowing that 450 would be halfway up, so I'm not halfway up. I'm about a quarter of the way up at 427. 384 again. And then 315. 187. And 56. All right, so this last marker here my pen's running out. Let me get a new pen. This last marker here must be 2200. All right. Or actually, I'm sorry. I just realized I skipped something. So don't make this mistake when you try yours. I accidentally skipped this line. So there should have been 2200 should have ended here, and I should have had a blank one here for 2300. So fix that on yours. Shove them all over once. I don't have an eraser for my ink pens, so we'll ignore that all of mine are just a little off. I'll just draw arrows to where they should go. I'm sorry. There we go. So 2200 should be right there. Okay, but we get the idea of what we were supposed to be doing. So, Now, they ask us to determine the practical domain. So the full domain, you see, I've listed values from 0 up to 2400. I can't go past 24 because the day clock cycles around, but also there's no one really in the parking lot at 1 a.m. or 2 a.m. or 3 a.m. So the values that make sense in terms of this context are the values between 700 and 2200, or 7 a.m. and 10 p.m. So um, I would list these as the values in the practical domain. Now, we could argue, again, there is some room for movement in practical domain because in terms of what makes sense. So these are the values where you would expect the output to be non-zero, where people start showing up for work at 7 a.m. and some people don't leave until 10 p.m. if they're using the library or who knows what they're doing after they get out of their evening classes. Now, I could say, any time is valid. It's just that for the first several hours in the morning, I would expect the output to be zero. So I'd have 0 cars, 0 cars, 0 cars, which is fine. And so in that case, you could argue that anything between 0 and 24 is acceptable in terms of the practical domain. But you certainly cannot have numbers bigger than 24 because they're not part of a 24-hour clock. Clocks would cycle after that. And you can't have anything before 0 as in negatives because they're not, again, time values. Okay. Now, in terms of discrete, we'll talk about discrete in a moment, but I've already listed these with the curly braces to indicate discrete. Now, time itself is not discrete. Time is continuous because you can go down from hours to minutes and seconds and talk about connecting your times. But I don't want discrete in this situation because I'm not sending somebody to the parking lot every second of the day. I'm just sending them on every hour and be like, count all the cars for me, dude. So that's why we're using discrete here, is because on the hour, we're able to pull a count of number of cars. We don't have a continuous count of the number of cars. That was not something that was within the budget. It's just a discrete situation for this data set here. All right. Now, cars. 0, 1, we have discrete again here. You can't have half a car in the parking lot. You can have one car or no cars. And then there are 600 seats in the parking lot, so we'll go up through 600 as our capacity. All right. So describe some patterns. So the number of cars increases until about 11 a.m. Then it decreases to a low at, let's see, 1, 2, 3, 4 p.m. Then it increases until 6 p.m. And then it decreases again until 10 p.m. So the number of cars increases in the morning, we'll say. Increases in the morning. Until 11 a.m. Then decreases in the afternoon. The number of cars increases again in the evening, probably for night classes or evening classes. Increases again in the evening. Sorry, it's hard to write the bottom of the page. My handwriting is getting a little sloppy. So the number of cars increases again in the evening, then decreases overnight. Okay, can the parking lot function be defined symbolically? So as an equation. And so this was data that we collected. I don't really have a pattern here that I can do as a symbolic equation. So no, it's not like our prices of gas where I'm like, multiply this by this. I don't have a process. So there's not a process to determine the number of cars in the lot, besides going out and counting them. For determining or predicting. All right, so there's no process for determining or predicting the number of cars. All right. Okay, so note that the graph of the parking lot consists of 16 distinct points that are not connected. The input variable is each hour on the hour from 7 a.m. to 10 p.m. And the parking lot function is said to be discrete because it is defined only at isolated, distinct input values. It's not defined between, these particular values. That's what it means to be discrete, defined for distinct, isolated points, not between these particular values. And so for discrete, we use those curly braces in our notation, and we use a list of values. All right. Caution. When we graph things, it's often convenient to connect points, but that creates a continuous graph. If you connect points, you make it continuous. This changes the domain from some values to all values. We need to be cautious. Only connect them when we want them to be continuous. Never connect your points in a discrete situation. Okay, moving to example 1 on page 2 of activity 1.1. Excuse me. All right. I think this is our Lake Placid data. It is at the bottom of page 2, but I'm going to go to page 3 because it's also there. And I can see it side by side with my screen here. And we need to graph this on an appropriately scaled and labeled set of coordinates. All right, so I'm going to need the date as the input, and I'm going to need the temperature as the output. Now, I don't really need to do 0, 1, 2, 3, 4, 5, 6, 7, because then I would only graph everything on just this little tiny slice. So I'm going to spread this out and do every other one, 0, 1, 2, 3, 4, 5, 6, 7. That way I'm not condensing it down to one teeny tiny graph. I'm just going to spread it across the available space so that it makes it easier to see the points. So I'm going to graph this and every other marker. So we have our 0, 1, 2, 3, 4, 5, 6, 7. All right. Now, up the side, I need to get all the way to 30. So I'm not going to be able to count by ones because I wouldn't make it. So perhaps we'll have to count these by, let's see. So 1, 2, 3, 4, 5, 6, 7 would have no way to make it, but 5, 10, 15, 20, 25, 30 would make it. But it would, again, put me in this little tiny chunk. So we're going to go by fives, but we're going to go every other one. So 0, 5, 10, 15, 20, 25, 30, 35. All right. And I guess I could label 8. I don't need it, but I can label the last one there as well. Okay, so let's start graphing. We have our 1. I guess our first one is 1 and 25. So 1, 25, 2, 30, 332. So hold on. Okay, so this would be 32.5. So 32 is actually quite close to that line between 30 and 35. Then 424. 523. So this is 22.5. So 23 is quite close to that. 627. So this line right here would be 25 plus 2.5, so 27.5. So 27 is just below it. And then 730. So I knew that each of these was counting by 5, and since we skipped one, half of 5 is 2.5, so each of these was 2.5 higher, and that's how I was able to estimate my points. All right, so there's our graph. I'm going to move the data off to the side. Determine the practical domain of the temperature function. Now these are dates. There is no date between them. 1.5 is not a date, so this is going to be discrete. And even though I do have 0 listed just to help us with our axes, 0 is not a date. So the first date is going to be 1 through, I had data for up through the 7th day. So sometimes when I do a practical domain, I can go, what the data says. I collected data for like a week. So I could go 1 through 7. Or you could also say, I don't have data for it, but maybe I could have kept my study going for a few more days and I could have went 1 through 31. But I know that for sure after 31, it's not going to make sense because 32 is not a date. So there are 2 philosophies for practical domain, and it's not like one's better or worse than the other. Although usually when we have data and we talk about practical domain, once we start making models from our data, we're going to make sure that we don't go too far past the edge of the data because our models are going to start to make bad predictions or extrapolations past the edge of the data set. So I'll stick with the 1 to 7 for my practical domain on this one, but just wanted to consider some other possibilities that we might want to consider in a different scenario. So practical range. Okay, so all of the temperatures were in this span. So if someone had said the temperature in January was 10, I guess I might have believed that, but maybe it's not possible. Looks like 20 is going to be around our low. So I would say it's between 20 and, 35. I can estimate these values a little bit, but we're just thinking like something in this span is going to say values between those are making sense in terms of the inputs that we have. So that's how we're getting the range, is we're thinking about the output values in that span as being values that make sense corresponding with the input values that we see. Now, you could pin it down a little closer to 20, what was that one, 22 or 23? And then this one, which was 30, nope, yeah, 30 was the highest one, I think, right? No, 32? Maybe this one was 32. Okay. But we can allow for a bit of variation, just kind of broadly spanning those values. Now, it occurs to me, as I am writing these, that I did not write them properly. So forgive me on this and we'll fix it. Practical domain needs to be a list if it's going to be discrete. So I didn't do a list, and that's my fault. Part of it is when I'm thinking about domain, I often do things that are continuous, and these are not continuous. When you're doing continuous, you need to list first and last only. But when I have a list, I need to have all values in it. So I didn't do that. So I got to fix these. Okay. So I needed to go 1, 2, 3, 4, 5, 6, 7. That's my practical domain. Or if I wanted it to be bigger, I could do 1, 2, 3, until I establish a pattern, 29, 30, 31. I don't have to list everything up to 31 if I establish a pattern that I'm counting by whole numbers, but I do have to actually list the values. So this here as well, let's say 20, 21, 22, up to 29, 30. Discrete is actually kind of a pain to list because it is a list of all values. If you can establish pattern, then you can shorten it with the dot 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 in between, but it is a list of all values. When we get to our continuous sets, which must have been in my mind as I was writing these down, then it is first value and last value only, and then it's all values between. But because I do not want absolutely all values between, I have to list a pattern to establish that I want only the whole numbers. In a different situation, maybe I would want 1, 1.5, 2, if I wanted by 50, but not in this case. I want whole numbers only, so I must establish that pattern. Otherwise, 1 to 7, you're like, if you just say 1, 7 with those little braces, it means 1 and 7 are the only numbers that you're allowed, and no 2, no 5, no nothing. So that was definitely not what I wanted. So we fixed it, and I apologize for not thinking clearly as I wrote them down the first time. So these are discrete. So our list needs to have everything in it. Oh yes, and is this function discrete? Why, yes it is, and it is because there is no date between 1 and 2, etc. So whole numbers only, they're distinct inputs, they are not connected. Dates are discrete values. Okay. Sorry, my book does not quite fit here. Let's see if I can push that up a little bit. No date between 1, 2, etc. So that's why it is discrete. The input set will usually be the one that tells us if it's discrete, which is the date in this case. All right, so number 4. The marathon function in activity 1-2 was defined by the function d equals 26 minus 6.5t, where d is the distance from the finish line and t is the number of hours you have run. What's the practical domain? Okay. We said it was between 0 and 4, and this is continuous. They're going to define continuous for us on the next page, but it was connected because I could run 0 hours. I could run 0.1 hours, which would be a few minutes. I could run 1.5 hours. I could run values in between, and I could not possibly list them all because I could run just a few more seconds and it would change the value. Okay. Now I can make a list of a few values, just not every value specifically. So this value, we'll call our function d of t is 26 minus 6.5 t, and we'll make a table. We don't need to do one at a time. And we'll evaluate the function d at all the x1 inputs in our table. And it says list 5 ordered pairs. So I'll start with 0. Okay. So our first ordered pair will be 0, 26. If we've run for 0 hours, we have 26 miles left to run. Then I'll say 1. So if I've run for 1 hour, I have 19.5 miles left to go. And then I'll say 1.5, because I get to make these up. It doesn't say what I have to do. I'm just going to emphasize the fact that I don't have to run for 2 hours. I could just say 1.5. So why not just illustrate that I can put a decimal value in here. 1.5 hours of running means I have 16.25 miles left to go. And then we'll do 2. Run for 2 hours, I have 13 miles left to go. 3, not 23. 3, if I run for 3 hours, I have 6.5. And just for fun, if I've run for 4 hours, I have 0. Interesting. I must have typed something wrong when I did this in the last section, and I apologize. 'Cause I got 0 here, and I thought I had a negative last time, but I may have not done something right, and I don't know what it was. But that's going to prompt me to bracket this dude. Because 4 hours, I finished the race, and I want to include that 4. Okay. So, all right. So I'll apologize for mistakes. They happen. And if you catch any that I haven't noticed, just let me know, and I'll make a comment about it. For the most part, we are on track here, and if we do make a mistake, we will fix it, and we will be okay. We are going to now sketch the graph of the marathon function by first plotting the 5 points from part A on a properly scaled labeled coordinate axis. So I'm going to pull my graph over here so I can see it again. 0 to 4. So I'm going to space these out probably by every other one is going to be one of my values. So I'll do 0, 1, 2, 3, 4, and this is in hours. And then this is going to be in miles left to run. And I got to get 0 and 26. So I probably should count by 5s every other one again. So we'll start at 0, 5, 10, 15, 20, 25, and 30. All right. So 0 and 26. Then 1 and 19.5. 1.5 and 16.2. Then 213. 3, 6.5. And 4, 0. Does the graph consist of just the 5 points from part B? So this is going to be no, because many other inputs could have been plugged into the function. Many other choices of input could have been used. Describe any patterns or trends. So the graph is decreasing at a steady rate. And the marathon function, as we were mentioning on the previous page, can be connected to form a continuous graph. So if I connect these dots here, it's continuous. And continuous means that I can visualize where other points would be along the pattern here, because the ones that were plotted were not the only points possible. There were more possible points. Okay, so now let's look at the gross pay function. All right, and our gross pay function, G of H, was 10.5H. And for our inputs here, I don't remember what we wanted. I got to go back and look real quick. Page 14. All right. Page 13. Okay, so they were up by fives. So we went 0, 5, 10, 15, 20, 25, and 30. Okay. So they would like us to, again, graph this function by plotting the ordered pairs. This time, though, I'm going to use technology to graph it. They're going to ask me to use technology to graph in just a second anyway. And I want to demonstrate that there is a graph happening over here. I can't see this graph very well right now, though, because it's not been properly scaled. So if I have a table of values entered, there's going to be a magnifying glass at the bottom corner of the table, which if you hover over it says zoom fit, and if you click on that, let me shrink this down just a tiny bit so my graph becomes wider. If I click on the zoom fit, you'll see that it resizes the window to best display the values that are in the table. And so this is what the function looks like. And I can see that if I scale this by, looks like these are 5s through 20, maybe every other one, and then my pay, that goes up to like 400. So I can scale those up by 100. Then I can get this graph to plot. So I'm going to use technology to eyeball what this graph looks like. And we'll do 5, 10, 15, 20, 25, and then I want, 200 to be about the middle, and I want 400 to be about the top. And then I can see that my graph, it's not going to hit 400 until it hits 40, so it needs to hit 200 about 20. So trying to draw a straight line, I need to get a ruler out because my page is held up in the air here to make it visible. But something like that would be a sketch of what we can see here. Now, if we wanted to plot our points a little more precisely, then yes, we could dot in our 0, 0. We could dot in 5 at 50.2 and so on to create each of our dots and each of our labels here. But most of the time, a quick sketch that we can see that we have the function increasing at a constant rate is going to be helpful, and the graph on Desmos created by technology is going to be more accurate than the one I draw anyway. So we're going to like to use our graphs created by technology to help us. Okay, so there's one of them. And then is the growth function continuous or discrete? And so if it was discrete, it would mean I could work for 5 hours or 10 hours, but I could not work a value between them. But I can work for a value between them. I can work for 6 hours, but do I have to work whole numbers, or could I work for 5.5 hours? Could I work for 5.1 hours? And would I get paid? The real question is, would I get paid if I worked for 5 hours and 5 minutes? Or would I not get paid the extra time unless I worked for 5.5 hours? But I would, I hope, get paid even for those extra minutes. The clock in, clock out time are going to contribute to my pay, not just by the amount of hours. And so if that's the case, and this is a continuous function. Okay, so we are paid for all values between all input values between 0 and 30, including fractional time. So I'm not restricted to the whole numbers only. It's really hard to see the bottom of my page. Let me see if I can push that down. So we are continuous because we're paid for all values between 0 and 30, including those fractional time inputs. We're not paid only for 5 hours and then not paid if you say 5 extra minutes. You should get paid for those 5 extra minutes. A couple cents at least. All right. So we'll continue graphing using technology. The the graph of the cost of the fill-up function defined over its practical domain. All right. And there are two graphs here. So one of the graphs is over its practical domain and one of them is over its full domain. So let me get the function showing up over here first and take off my table. This function was c equals 12.6p. Now, by default, when I graph something in Desmos, it's going to graph over its full domain. It's not been restricted. If I want to give it a restriction, then I need to enter the restriction in inequality notation. So first of all, I'm going to use a note, which I can use by typing a quotation mark or clicking the note button here. And we're going to remember that the practical domain for this situation was between like $2 and $5 was the values for the price of gas, I think, that we had decided in one of the earlier sections. Now, this is an interval, and this is an interval of x values. And so the lowest of our x values is 2, and the highest of our x values is 5. So currently, we have expressed this in interval notation. Now we're going to change it into inequality notation. So the lowest of the x values is 2. Give me just a second. I have to type a less than or equal to sign, and I have to paste one in because I can't type it in a note. Okay, so 2 is less than or equal to x is less than or equal to 5 would be the inequality notation for the same interval. So this practical domain says that 2 is the smallest value and 5 is the largest value. And this is domain, so x is the variable for domain. And so that x value for our domain is in between 2 and 5. We'll talk about intervals more throughout this chapter. We have a section on intervals versus inequalities towards the end of the chapter, and we talk about inequality equations. But we'll just have to work and try to express our domains both ways so that we can talk about them and use the inequality notation to restrict the domain. So I'm going to write right after my function a curly brace. Now this curly brace does not mean discrete. It just happens to be Desmos's notation for restricted domain. It's definitely a continuous domain because I'm writing it in an inequality notation. So 2 is less than. I'm going to hit the equals key. And when I hit the equals key, it's going to pop the equal bar right underneath the inequality for me. Less than or equal to x is less than, or hit the equals key, equal to 5. And when I graph this, first of all, it's not understanding p. So let me write this as c of p. Oops. No, that wasn't the problem. My apologies. The problem was that it didn't understand why I called the independent value p here, but I called it x over here. So actually, this should have been p the whole time since x is the generic version of the independent variable, but the specific version is p here. All right, so now I can see that it shortens the function and graphs it just over the practical domain. And that is how the function looks here. So I can get Desmos to draw a graph over its practical domain if I write the practical domain in inequality notation instead of interval notation, and if I use those curly braces to restrict the domain. So, tiny bit of taste of this. We'll be doing this more this chapter in sections 115 and 116 specifically, but as we work towards there, we'll get some practice along the way. Okay, so they already had created those two graphs for us, and it said using technology, so I figured I would help with the Desmos technology for creating those two graphs. Okay, so number 6, again, is all about rescaling things for this same function. Calculator rescaling is weird. Rescaling for our function is going to involve the graph settings button over here. Let me just make my window a little bigger. And if they give me an xmin, xmax, ymin, ymax on the interval of -10 to 10 for input, that just means that they want to see -10 to 10 on the input scale And I don't know if they want in their Y scale. Likely not negative 10 to 10 because the outputs are larger than that. So I'm just going to leave them what they were at the default. I'm going to take off the restriction so we can see the full function graphing out there. So anytime they talk about their window or their X-min, X-max, that's your X-min, your X-max, your Y-min, your Y-max, so that you can graph on the window that they are talking about. So in the graph settings with that wrench icon up there. Okay, so how does a graph that we see here in part B compare to graph 2 in the previous page? Should be the same graph. So part C, if you want to write in, this graph that we created on our decimal screen should match the one that we were seeing over here on paper. Okay. In the last part of our section, we're defining functions as summary, writing functions verbally, symbolically, numerically, and graphically. There is an example here of the hourly pay situation where they did the verbal, the symbolic, the numeric, and the graphical. So we're going to do the same thing with this new situation about sales tax. If the sales tax in your area is 6%, define the cost 4 different ways: verbally, symbolically, graphically, and numerically. So the verbal is going to be just a statement, a sentence about what we have to do in order to compute sales tax. So verbally. Okay, so sales tax is 6% of the cost of an item. So we are going to multiply 6%, which converts to 0.06 by the cost of the item. To compute the sales tax owed. So explain what it is that you need to do to go from the given information to the result that you want, the amount of sales tax that you owe. I know it's 6%. I got to take that 6% or 0.06 and I got to multiply it by the cost of the item. All right, so symbolically, I need to define some variables here. So let's use T for tax and X for the cost of the item. So they didn't give me a variable here, so I'm going to use X for the cost of the item and T for the tax. X for the cost of the item and T for tax. So symbolically, my tax T is 0.06 times X. And then numerically, we've got ourselves a table here. If I write this in function notation instead of equation notation, I would have written this as T of X equals 0.06X. Either one could be symbolic. It's just one is written as an equation and one is written as a function. If I want to use an autofill table, I have to use function notation in Desmos. So I'm going to type this in function notation. So T of X equals 0.06X. Then I can make myself a table. And I can plug anything I want into the table, but I'm going to get to autofill with T of X1. Right? Name of the function is T. I want to put all the X1s into the function. So let's say the item costs $5. So if it costs $5, I owe 30 cents of tax. I can't read, apparently. I owe 30 cents of tax. If it costs $8, I'm making up values here, it costs then 48 cents of tax. Or if it costs $11, then I owe 66 cents of tax. or $14, then I'll owe 84 cents of tax. These are just counting up by 3. Do you notice how when I hit enter, my table's autofilling for me? But let's say I don't want to count by 3 anymore. Let's say I want to jump to a new value. Let's say it costs $20. Then I owe $1.20 in tax. Let's say it costs $25. I'm making up the inputs. There were no inputs given to me here, so I can pick whatever I want. It costs $1.50 in tax. What if it was $40? Then it would be $2.40 in tax. What if the item costs $50? Then it would be $3 in tax. What if it cost $100? Then it would be $6 in tax. What if it was $150? $9 in tax. And what if it was $200? Then it would be $12 in tax. Okay. You might not have went so high. You don't have to count by any specific number. I just picked whatever I wanted to for the input in order to compute the output. Okay. Now, graphically, I'm going to use decimal or technology. Now I can see a tiny little something on this chart right here, but remember, that this graph has been rescaled for a previous situation. So what I see here is not what I want to draw on my page. I'm going to rescale for my table with the zoom fit, and if I don't have a table, then I could rescale manually. But the zoom fit graph will show me values for the current situation. So I am going to draw this like this. And just a rough sketch, when I start off here at 0, if I ended here at 200, that would be my scale across the input, but my 200 ended up here at 12. So I'm only really roughly scaling this, but by putting a tiny bit of scale here, it helps us see that it's not like 200, 200 or 12, 200. It's 200 across the x-axis while only 12 across the y-axis. So just a little bit of scale to help us figure out this picture. So I'm only kind of plotting this point, and I don't have 0, 0 on my table, but if you do put 0 into your function, 0 times 0.6 is 0, so my other point's down here. Okay, just a rough sketch with a tiny bit of labeling gets me accuracy, and it helps me get my technology-assisted graph. All right, and then we have hit our summary. So make sure you read through your summary, and I'll get on to the next section.